Okay, so the recording has started. We can start today's session.
Okay, just a minute. Perfect. So, can you see my screen?
Yeah, your screen is visible. I guess everyone should be able to see that.
Good. So, yesterday we talked about qubits and quantum superposition. And I shown you yesterday that how this superposition is going to play a very crucial role in the quantum computing, because if you have just a quick recall that if you have only let us say one electron, and simply talking about a one qubit, then in the superposition state, I need to define two complex quantity A and B. And similarly, if you have a two electrons means two qubit, then I need to define four complex number to represent the wave function psi. So idea was that in this superposition state, lot of information is available. And then I discuss also a bit idea about how this computation can be done, and through interference, how we can get the correct result out. So that was something we did in the last class. And then also we discuss about the Bloch sphere. And this we understood with the help of the Stern-Gerlach experiment, that how on the Bloch sphere we can show the spin state. Now I took the example of electron spin, so we can show this spin state on this Bloch sphere, and this spin state is going to rotate, and during the rotation, so if this is the spin state in n direction, then this will rotate, and these are some directions I mentioned, like 1, 0, okay. And let us say think about this is the x-axis, y-axis, and z-axis. Then when the spin, this spin vector or the tip of the spin, when comes to this point, then we call it as the 0 state. When it comes here, we call it one state. When it come to this location, okay, then we call as a SX plus state. When it comes here, then we call it is the SX negative state. Exactly, and correspondingly here also. So accordingly, we can represent
SY plus
a negative. Yes. So this rotation, the rotation of this spin vector, okay, along now around on the sphere. Now, so the tip always move on the sphere. Okay, this is going to represent different orientation, And accordingly, we can define these our different spin vector states. Okay, Sy, Sz. So this we call as the Sz negative, and this we call as the Sz positive. So we will use this concept, the blow-sphere concept, also today to understand the gates. So when you talk about quantum gates, so today's topic, as I mentioned, that we will focus on the quantum gates. And again, if you look back, then in the classical computer, you have a transistor, and that this transistor analogy here is actually electrons in the two states, spin down and spin up. So these transistors can be used to make different types of gate. Similarly, these electrons are qubits. So technically, I will use these states. So I will use this state to make the gate. And those gates I'm going to call as the quantum gates. So we will build some bit concept here, and then slowly we will now go to the. So we'll start with the simplest gate, and then go to the uh, difficult gate, which are of course 2 qubits gate and 3 qubit gates. So let us start now in small steps. So when you talk about quantum gates, so they are nothing but a unitary operation. They are nothing but a unitary operation. So when you talk about unitary operation, then we will definitely talk about the unitary operator also. So unitary operators symbol, I'm going to use U. Okay. So this is actually defined as, I mean, I can say that the U preserve the norm. Norm means I can say total probability of a quantum state. And we define this as this mathematical equation that U dagger U, or U and U dagger, this is equal to I, or also the U dagger equal to U negative. So this is nothing but a what we called conjugate transpose, correct? Okay. So what it means when I say you preserve the norm, okay, or total probability of a quantum, what it means. So you can think like here, when you're going to apply a unitary operator on a state called, let us say, n cap on this state, what it will do? Okay, you think like it is going to rotate. This is going to rotate the point on the surface of the sphere. So you can think of a quantum state like a point here on the surface of blow sphere. And then what does this unitary operator going to do here? So unitary operator is like a rotation of this vector on the surface of the sphere. And in this process, you can see that the radius of this vector never going to change. So it will simply going to rotate on the surface of the Bloch sphere, but the radius, and the radius here is nothing but the norm. And norm nothing but the probability. So unitary operator is simply going to rotate the vector in some direction. And in this process, you can see that the length of this vector, that nothing but the norm or the probability of that wave function, that will never going to change. And so what is changing? Only the direction. So something is changing, that is only the direction, not the norm. So that's why these unitary operators, now how they are defined in the quantum mechanics. They're going to preserve the norm. Okay, they will preserve the probability. So in the case of spin, we can think that they are simply going to rotate the spin vector. Not only spin, I mean, so if you look at in quantum mechanics, so there are many different types of unitary operators you can think. So for example, think about a translational operator. I'm just giving some example. A translational operator means, think about you have some wave function at this location, and when you apply some operator, and this wave function is then going to shift to new location. Then I mean, let us say I have an operator A, and I'm operating on the wave function psi x, and after the operation, the wave function moved to the x plus A. Now see, I mean, we can I can prove that this operator is going to be a unitary operator. How to write down? Now, I think this is the some graduate level problem or the MSc problems. You must have done this. So when you're going to do a Taylor expansion of this function, okay. So this I can write like psi x plus a time d psi by dx plus a square by 2 factor and d square psi upon dx square and so on. And here, if I take psi x common out, so this is going to become 1 plus a time d by dx plus a square by 2 factorial. And then here the psi x will be, I can take out. And look at, if you look at the exponential expansion, Taylor expansion of e power x, how to write down 1 plus x square by 2 factorial and so on. So technically, if I call this as the x, then this is nothing but actually a e power a d by dx into psi x. So I have written the same thing in the operator form. So from there, I can certainly say this operator a is nothing but equal to e power a upon into d by dx. Look at the momentum operator along the x-axis. How do you define? Minus I h cut and d by dx. And from there, I can find this value. This is going to be iota p upon h cut. And you can see that from there, this operator a is going to become e power iota p time px time a upon h cut. So this is the translation operator. And I can prove that if I take a dagger So this is going to become e power what? Minus iota and px dagger, and a is some number, so it will remain as such, and h cut. And you know that the px is a Hermitian operator, so this is going to be a px only. So this is nothing but e power minus iota pxe upon h cut. And from there, you can see this a dagger a will be equal to I. So I can certainly say this a dagger is going this a is a unitary operator. This is nothing but a unitary operator. So I'm just giving some example, okay? So just to let you feel comfortable that what unitary operators are. Even you can talk about time translation operator, okay? Or time evolution operator, for example. So in quantum mechanics, these unitary operators play a very crucial role. So time evolution operator means if you apply some operator on the wave function, which is a function of time, then this is going to change to t plus t naught. And the same logic you apply here, expand it. So it is going to be a 1 plus t naught and d psi upon dt n plus t naught square by 2 factorial and d square psi upon dt square. This is going to be 1 plus t naught and so on. And psi t will be common out. And this is nothing but a e power t naught d by dt into psi t. It means this time translation operator will be going to be equal to e power t naught d by dt. And you know that the energy operator E defined as a iota h cut and d by dt. And from there you can see the t operator become e power minus iota e and t naught upon h cut. In some books you write the same thing like a e power minus iota h cap t upon h cut. So this is very popular now. This is called the time evolution operator. So when you're going to apply this operator on the wave function, so the wave function will be going to evolve in time, okay? But the probability or norm of the wave function will never going to change. It will preserve the norm, okay? And while preserving, it will going to rotate or it will going to evolve the functions. I will not call here rotate because this is not a vector quantity here now. I mean, not a physical vector. But here, what we are concerned about the rotation operator. Because in our case, rotation operator, because in our case, the spin is rotating. So spin rotating means I have a vector, let us say rotation operator, let's R, operating on a state psi, which is a function of phi, let us say. Then this is going to rotate and it is going to go to another angle phi naught. And you can see that the same logic you apply, this is going to be e power phi naught into d by d phi into psi phi. And from there, you can see this r cap can be written like a e power phi naught and d by d phi. Now, if you talk about orbital angular momentum, because the functional form of the this operator is known to us. So think about the LZ, nothing but a iota h cut and del by del phi. And from there you can see this r cap is going to become e power minus iota LZ into phi, means you can say phi naught also upon h cut. With the same analogy, if I take a same analogy and go into spin, apply the same thing for the spin. So for the spin, I can say R, no, I will call R phi, I mean rotating by an angle phi. And here I will call, let us say theta or phi, whatever you can use, a symbol doesn't matter. So this is same logic I apply, it become a minus iota, and it will be a SZ into theta, okay, upon H cut. Now, it is in one direction particularly, but in general, this R theta written like a e power minus iota, it is going to be a Sn dot n into theta upon H cut. Now you can think that this quantity can become sometime Sz, this quantity can become sometime Sx, this quantity can become Sy, or maybe in some time in maximum location, you can think that this is written also in this format. So when we talk about rotation, okay, so think about our this Bloch function. So if you want to rotate this vector in this hyperspace, okay, so then I need this operator. Depending upon the value of theta, okay, you will going to see the different rotation then in this case. I hope if it is clear up till now.
Yeah, hello, Sugam.
Yes.
Yeah, so the theta is different from the geometric theta, right?
No, this is same, yes.
But when we are rotating, it could be a change of theta and phi.
Yes.
So when we are rotating about a particular axis, if you refer to the spherical polar coordinate system, both theta and phi can
Yes, it will
come.
come. I mean, what I'm trying to say here, okay,
Yeah.
I have not yet completed the whole part.
Okay.
Okay. So when you going to write down this whole thing, okay, as a unitary operator, okay,
Yeah,
that is
yeah.
the rotator that is going to rotate the whole system, okay.
Mhm.
So that unitary operator, okay, let us say of a single qubit, that is written like a e power iota phi into, let me call this r and theta, okay. So this is how it's going to take this value.
Yeah. So my confusion was here, we are only changing theta, right? As per the notation, but phi can also change, no?
Yes, this is only for the theta rotation.
Okay.
If you want to include the phi rotation, then this is the complete unitary operator. So if you want to rotate also in the phi direction, okay, then this is the, so this include the rotation in 3 dimension, okay, including theta and phi. But what I'm telling here, this is only now about the rotation along the one axis, theta.
Okay.
Okay. And now you can see these are the unitary operator, and you will see from there, I mean, I can make a different types of gate. In fact, now this r and theta, if you open this, and I will not solve, maybe you can try to now figure out. So this is going to be a cos theta by 2 identity operator, and iota times sine theta by 2 and sigma dot n. And of course, when you're going to have a complete rotation in the 3 dimension, then it must be written like a e power iota phi, and then cos theta by 2 I cap minus iota sine theta by 2 and sigma dot n. And here what we can do, we can define different types of gate by choosing the values. Okay. So I can take theta, I can vary. Okay. I can vary the phi, and accordingly I can acquire the different configuration. Okay. So for example, think about if I take phi equal to pi by 2, I'm just going to simplify this equation, and then theta equal to pi. Okay, and accordingly you can see that when you put phi equal to pi by 2, okay, then this is going to be a simply iota term. And when you're going to open this, I mean, this is something you can do, and this is going to become simply a sigma x and an x and sigma y and when y and sigma z and nz. It is mathematical, but I will explain you how physically we're going to realize. Okay, and then you can set the value of the nx, ny, and nz. Okay, so for example, if I'm going to set value 1, 0, 0, okay, I mean along the x-axis, then this u is going to become simply sigma x, and this is 0, 1, 1, 0. Okay, and this is what is called the poly x gate. When you if you set this n cap, let us say 0, 1, 0, then you're going to get the sigma y, and this is what going to set the 0 minus iota, iota 0, and this is what is called the poly y gate. And similarly, you can construct other gates also, and sigma z gate also, that is the 1, 0, 0 minus 1, that is called the poly z gate. Even so, little bit, let us talk a little bit on this poly S gate, because this is more or less mathematics. Exactly how we can realize these gates. Okay, that is the more important for us. So you can see here, the first of all, when you talk about a sigma x or poly X gate. So I said that this is a X cap, and this is nothing but a 0, 1, 1, 0. Little bit mathematics. Now, if I have a BLOS function here, and in this BLOS function, then okay, let me start with the Z gate. That is much simpler to understand first. So Z gate means Z cap. Okay, better to start with sigma x only. So poly X gate. So this is a X cap equal to 0, 1, 1, 0. And look at now, if I, in the Stone-Gala experiment, I had applied this magnet in Z direction. It means the atoms with a non-zero magnetic moment, when they're going to pass through, so they're going to split in two parts. Okay, so one correspond to the spin up and down, which you can call as a 1, and this you can call as a 0. And I already shown you that this is what is the 0, and this is what is called 1. In this diagram. And now look at, if I apply this x on the 0, okay, so 0 is the basis state. So x means 0, 1, 1, 0, and this is going to be a 1, 0. So this is going to make a 0, 1, mean nothing but a 1. So technically what this x is doing, this poly X gate is simply converting
Not
0.
gate. Not gate.
Exactly, it's a NOT gate. That's correct. So it is acting like a NOT gate. So it will simply going to flip the spin. Okay. So earlier it was along this direction, it will now going to flip on this direction. Okay. So it is going to flip the spin state from 0 to 1 direction. So this is how this X gate can be understood. Okay. Similarly, if you look at the sigma Y or poly Y gate, what is doing? Look at Y gate, nothing but a 0 minus I 0, and look at when the Y operate on the 0. So means this is a quantity you're going to have, and when this is going to operate, so it is going to make what? It is going to become 0 and iota. So this is iota 0 1, nothing but iota 1. So it is simply going to add, it will flip the spin along that direction and also going to add a phase. Okay. And we will see that how to realize the poly Y gate also, but you can see that it is simply adding a phase.
A to the power I pi by
Yes, say again.
A to the power iota pi by 2. Yes.
So it is just adding a phase. Similarly, if you look at the sigma Z now, that is the Z gate. This is nothing but a 1 0 0 minus 1, and look at what it does. So Z operates on the 0, and it is going to be 1 0 0 minus 1 and 1 0. So this is going to be a 1 and 0. Nothing changes. Okay, so this is not going to make any change on the 0, but now it is going to operate on the 1. Then you can see the difference. It is going to become minus. Okay. So we will just try to understand these. There are many types of gates we can manufacture. Okay. But technically, our task here should be to understand how to realize in the laboratory. Let us say if I want to construct some gate, okay, then how we can do that, how we can really construct such gates in the lab. Okay, so then I will come to the other gates also one by one. So for example, let us say that realization of X gate. So how we can construct X gate in the reality means technically what I want 0 to convert into 1 or 1 to convert into a 0. This is what is our task here all about. So how we can do it? So I will start with the very simple example. We will again, let's take electron in, so consider electron in a magnetic field. Let us say magnetic field is 1 Tesla. And you know that if you place the electrons in the magnetic field, then Zeeman splitting will take place, correct? And because of the Zeeman splitting, this quantum state is going to have a separation. So this is the 0 state and this is the 1 state. Or maybe I can call like this, sorry, like this. Can you please mute your mic? So you see that what happens? I mean, so this electron has a spin. So electron is a spin, okay, is a
Would
magnetic
it be
moment.
would it be better to call I mean atom in a magnetic field rather than electrons in a magnetic field?
Both, both
uh,
you can, both I can say, because for example, in my experiment, I'm going to use bare electrons.
I mean, realization of a single electron. I mean, okay, fine.
It's much
But,
simpler actually, okay.
mhm.
For example, no, when you talk about, let's say, ion trap, okay, or punning trap. So in the punning trap, I can trap electrons directly. It is true also for the same thing also applies for the atoms also. So electrons in the atom, same logic applies, but both are practically feasible platforms. We can trap atoms, and we can just use electrons of the atoms to as a qubits. Or I can trap electrons also, bare electrons also in the trap, and I can use this electron as a qubit. And this is what I am doing at now at our institute. We are working on the single electrons.
Okay.
Sir, is the
Or
magnetic field?
I mean, you can also think about that there is electron here, and it is going to have a spin. Yes, please. What is the question?
Oh, sir, is the magnetic field produced by the vibration of electron, since it is a charge, is less than the magnetic moment produced by the intrinsic spin itself? Like how then in that case, like in case of if electron beam is moving, then there is no meaning of this Zeeman splitting. Like that's why your neutral ion is used in Stern-Gerlach experiment instead of a moving electron beam, because the magnetic field produced by the moving beam is strong enough that the effect of magnetic moment due to spin is like most of the, like you can say, zero. Like in that in the pinning trap case, is the since electron is not completely rest, since they are jiggling somehow, then they also producing some kind of a magnetic field. That magnetic field is less than the magnetic moment produced by the spin.
Let me call here electron in a homogeneous magnetic field. Okay, then that problem is resolved, correct? What you
Yes,
are
yes.
asking.
Then that's
So we are using a homogeneous field completely. And when you place either this bare electron or maybe this atom with the electron having a non with the spin magnetic moment. So the situation is that is something like this again, that the magnetic field is there, and this electron with a spin is going to act like a bar magnet with the magnetic moment, and corresponding the Hamiltonian in this case is going to be a minus mu s dot b, and this mu s nothing but a minus g e by 2m into s vector. And here, if the magnetic field is only, let us say, along the z direction, then I will be only going to get this part. And look at here, this mu sz, nothing but a minus g e by 2m sz
MS.
component. Exactly. So you can put it here. This is going to be a plus, and this is going to be g e by 2m e and sz. That is the Hamiltonian. And when you're going to find the expectation value of this Hamiltonian, that is going to give the energy. Energy will be G. So this Sz on operate on the psi is going to give a ms h cross. Okay, so this is going to be a G into ms. And h cross will come here. That is going to become mu b, and there will be B field also here, and B. So this is the energy term you're going to have. And if L is 0 and spin is only non-zero part, then in that situation, G will be 2. Okay. And of course, for spin half particle, the ms is going to be a plus minus half. And you can see that this energy, the E1 will be then going to be a half mu b b, and this E2 will be minus half mu b into b. So you can see that the one level will go up by a quantity half mu B into B. The one level will go down with the quantity minus half mu B into B. And these are the two states. So when you're going to place electron, whether it is a bare electron or unpaired electron in an atom, in both the situation, this electron spin, which is going to behave like a bar magnet, and this bar magnet when to going to place in the magnetic field. So, and the magnetic field is homogeneous, as I mentioned, then this spin is going to align itself into possible directions, and as a result, these two states are going to be observed. One is a high energy state, other is a low energy state, corresponding to the two spin state, 0 and the 1. Okay, and the separation here you can see that is going to be a mu B into B. That is the delta E. So that is the one task here, that when you going to place, I'm trying to explain you that how in the laboratory we're going to produce, okay, these X gate, let us say, for example. Okay. So so these are the spin separation which you're going to have here now. And now you can further see that yeah. Yeah. So these two
Oh,
spin states are
what
there.
if we,
And let us say if the magnetic
Professor,
field,
what if we try to include the nuclear spin in case of an atom?
then in that situation, the net spin will going to be a combination. Okay. So then you have to find the net spin.
Mm-hmm. Okay.
So then you cannot isolate simply now. It depends upon the coupling. Okay. So let us
Yeah,
say
so
if
to
it, let us say
better
it,
find.
if you have, let us say, a spin also, and let us say nuclear spin also, and the applied field is very weak. Okay. Even if you don't apply anything, even then the spin and this nuclear spin going to couple together. Okay. And because this coupling, then you will going to see hyperfine splitting.
Yeah.
Then you will talk about the hyperfine levels in that situation.
Okay. Okay. Thank you.
So here what I'm saying that think about the situation. There is a 1 Tesla magnetic field. Then corresponding, if I calculate the h nu, because you get the energy here, you multiply with the mu B and the B 1 Tesla and h nu. And if you calculate nu, this nu is actually a 28 gigahertz. So in principle, what I can say that there are two states, spin states. So one is a 0 state and one is a 1 state. And the separation here between these two states is correspond to a frequency of a 28 gigahertz. Now see, if I shine a microwave on this system, okay, and if the frequency of the microwave is exactly 28 gigahertz, and then let us say the electron is already in the ground state, I mean up spin state, okay, then what we'll do, it will going to absorb this 28 gigahertz, and as a result, it will make a transition to the up state. So you can see that if I shine a photon on a 0 state, you will get 1 state. So in the case of electrons, for example, in this case, so if I want to flip the spin of electrons, then I need a microwaves. So technically, a microwave can do this job for me. It can make a transition from 0 to 1. For example, if you are working for the Zeeman levels, Zeeman splitting, and not going for the spin orientation, but you want to make a transition of atom itself in the Zeeman levels, okay? Then depending upon the gap, you may be working in the optical radiations, okay, or laser light. So in principle, I can say doesn't matter what kind of system generally you have, mostly laser and or microwave, they can do this job. For example, in the superconducting qubits, microwave works. In the case of ion trap, where you trap the ions and utilizing the Zeeman splitting, then people use laser to do this transition. And if I use the electron, then I will use the microwaves. So here the microwave can do this job for me. I hope this part is clear. Now, but there is a catch here. Okay, this is not so straightforward and simple, because if I shine this photon, and if these photon are no, continuously falling on the electron, then this electron is also, I mean, this process, what I have shown you, this process is called absorption. But imagine that if electron is already in the high state, is already there, and then if you shine a photon of again 28 gigahertz, then what will happen? This is going to cause a stimulation, correct? So same frequency photon can cause absorption, and in this process, electron going to go from the ground state to a higher state by flipping its spin. But on the other hand, if electron is already in the upper state, and when you're going to shine the 28 gigahertz radiation, then it is going to cause the stimulation. And in this process, this electron going to come to the ground state by again flipping the spin. All right. And Einstein, he did a thorough study of this emission, absorption and the stimulation, both. And then he come to the conclusion that, if you look at the probability, okay, so the probability of the getting one state, okay, means one kam milega, when you're going to get the one, when the electron will going to go from 0 to 1. So probability of getting one, you can go to this now mathematics and theory. So this is the probability is going to be omega t by 2, where this omega, maybe I can call omega r, and this is called Rabi frequency. And t here, nothing but a interaction time. Or you can say pulse duration. For how long time you're going to shine these photons, for how long the pulse will be there. In general, Rabi oscillations frequencies are very complicated expression to calculate, but in short, I can say with a good approximation, this is actually equal to mu time B1 or B upon H cut. And the most difficult task is to find these quantities, the mu, that is called the no, I'm sorry, that's correct. It's actually not mu, but it's going to be mu B, that is the Bohr magnetron. And this B1, the magnetic field you apply, and H, of course, you know. But what I'm trying to convey here from this equation is the following. Look at here. If you plot these oscillations of the probability, then this is going to be sinusoidal form, but only a positive quantity. So this is how the probability of getting one is going to show up. So you see that if the photon which is shining here or microwave is shining here, if this is going to remain there for a very long time, then what will happen? Initially, the particle will be in the ground state, then it will come to the one state, again it will come to the ground state. Again, I mean, in this case, you can see what is going to happen. This particle will keep now going up and down, up and down, up and down, up and down. So what I want to do, I want to convert 0 to 1. But if I shine the photon and photons are exposed for longer duration, then what will happen? 0 will go to 1. And then after some time, the 1 will come to 0. And again, 0 will go to 1 and so on. So this process up and down will keep going. But that is not reliable. I want surety that 0 goes to 1. So this is the point. See here, this is the point where 0 become 1. This is the point where the 0 becomes 1. So I mean, I have to shine these photons only for this much time. So if I shine, so how I can do this? So that is called pi by omega. I mean, when you calculate the time will be a pi by omega. So it means generally we call this, I mean, and according to this time you can calculate. So if you shine microwave only for pi by omega time. Okay. And then stop the pulse. And then you stop the pulse. Don't shine anything after that. So what will happen then? Then system in 0, and then you shining some photons, but only for the pi by omega time. Then after that it stopped. It means now you are already in the 1 state. So you have to make sure that you shine the microwaves only for this much time. Okay, and then you have to switch off the microwave source. Then this will ensure that the system has a high probability to go from 0 to 1. And this is nothing but a Pauli X gate. I hope this is clear to everybody, how experimentally in the laboratory, how we can do, how we operate. Okay, so when I say Pauli X gate is nothing but actually shining microwave or shining laser light for a time period of a pi by omega. And generally we call this as a pi pulse. The term we use, pi pulse. So we say 0 will go to 1 when you're going to use a pi pulse. Is this fine? This visualization, how to create Pauli X gate in laboratory?
Yes.
Perfect. Now, in general, what happens that, for example, let us say this is a magnetic field.
Sir, can you repeat it because I missed her due to network.
Which part?
From where you have said if you sign through microwave only for.
Yes, I mean saying ki, if you shine microwave only for this much time, it means ki when you shine the photon only for this much time, then at this time the probability will going to be maximum for the state 1 to reappear. Okay. After that, you have to stop the pulse. It means after that, you're not shining the photons. Then this 0 will going to convert into 1, and it will again become 0 if you keep shining. Let us say if you shine up till this time, that is called 2 pi by omega. Okay. Then this 1 again going to become 0. Okay. So if you shine, and this is pulse called a pi, this is called pi pulse. So if you shine pi pulse on the 0 state, then you will get a 1. Similarly, if I shine pi pulse on the 1 state, I means this much time only, then you will get a 0. Okay. So this is how this NOT gate works in the quantum computing.
Yes, sir.
And I mean, so this looks so simple, but this is not so obvious. Okay. Generally, what happened? There is a magnetic field you apply. Okay. And this is z direction. And let us say this is the y direction, and this is the x direction.
Yes.
So what we do generally, we shine photons in this direction along the
Why?
xy plane. Okay. I mean, you can't say what is x and what is y, correct?
Yes, sir.
So generally, we shine the photons in the xy plane to make sure that the magnetic field of EM wave is parallel to the applied field. Okay. Then only the interaction will be going to be maximum. Okay.
Yes, sir.
And look at here itself. Now, if you say, if you rotate or if you add phase of pi by 2,
Yes, sir.
in the microwave, so if you add a additional phase, and this is very simple. I mean, but generally what happened that experimentally you have a master source, master oscillator, and from the master oscillator we control all the pulses. Okay, the timing information is controlled by the master oscillator. So this is going to control all the signal generators. So the one signal generator going to give the pulse for the sigma x gate. And similarly, I can produce second pulse, okay, at any different phase. I mean, a phase I can vary. So if I add phase of, let us say, pi by 2 in the microwave, okay, then that is going to, I mean, so the same phase I can, I'm shining one radiation, and then I can split, maybe I can just take a microwave and then I can split in 2 parts. So this one can use for the X gate, and this one I can pass through a phase shifter. Okay, and then I can again shine this photon. Okay, so this can create a Y gate. Just you rotate the phase of the EM waves by pi by 2. Okay, and you can see that this is going to act like a sigma Y gate. So this is how physically, or on in the ground, generally we're going to observe this phenomenon. I hope up till here it is clear to everybody.
Sir, can you please explain master oscillator again?
I mean,
How
so
it works?
see, it is like no, you have only one clock, or I can say maybe a master clock. Okay, and this master clock is going to uh, it is something like there's a one master, and let us say 2-3 people want to start their race, okay, in the ground. And if you leave them on their own choice, so they can start with their own will, correct?
Yes, sir.
Okay, so let us say person 1, person 2, person 3. If there is no control on them, so maybe he will start now, he will start maybe later, or he can start sometime later, okay? So if there's a
Yes.
master, the one person is there, okay, he will say 1, 2, 3, now go, okay? So the master, I'm giving analogy to you that master clock is actually a master who going to synchronize, okay, timing of every instrument. So if I'm using, let us say, one signal generator, another signal generator, okay, third signal generator, okay, and I want to produce pulses out of this, and I want to give these pulses to our system, then I want to synchronize. Let us say I want that this one gives pulse only 1 nanosecond later than this one, okay? Then I must control all this instrument by a single instrument, na, correct? Then I will
Yes,
say,
sir.
okay, now you go. After 1 nanosecond, you also go. After 2 nanosecond, you please also go, okay?
Okay. Yes.
So they
Yes,
all
sir.
should be controlled by a single master clock. So generally,
Yes, sir.
for this one, people use rubidium atomic clocks, okay, which synchronize everything. So if you not have any experience, then just keep this idea, the way I told you about three person going to start a race, and then one master sitting behind, he going to uh, control them, okay,
That
when to
time.
start.
Yes, sir.
Okay.
Yes. Thank you, sir.
So we were talking about this gate, okay, and let me summarize. So we're talking about a single qubit gates. And in this, I talked about poly X gate, nothing but a 0, 1, 1, 0. Then I talked about poly Y gate, nothing but 0, minus iota, iota 0. Then third, poly Z gate, nothing but 1, 0, 0, minus 1. Functions already know. This is going to make 0 to 1 and 1 to 0, correct? Clear to everybody?
Yes, sir.
Similarly, you can think about Y also. You can just write down for the Y and Z, everything. And I can mention few more gates. Now, another very important gate that is called a Hadamard gate. Symbol we use H, very important in the quantum computing. And I will tell you how to realize this also, okay? In the above equation, जो मैंने लिखा था, just put this now n as 1 by root 2, 0 and 1 by root 2, okay? And you will see that that u is going to become a 1 by root 2 and sigma x plus sigma y, and then nothing but a 1 by root 2, 1, 1, 1 minus 1. That is what is called the Hadamard gate. What it will do, let's look at. If I operate H on 0, okay, again, let me draw that sphere. So when you're going to, this is 0. So when you're going to operate on 0, what it will make? Look at 1 by root 2, 1, 1, 1 minus 1, and this is nothing but a 1, 0. This becomes a 1 by root 2, and this is become 1 and minus 1. This is also written like a 1 by root 2, 0 plus 1, because 0 is 1, 0 and 1 is it will be a plus. It will be a plus. Correct? It will be plus. So this is the what you're going to have. So what are you getting? Okay. So when this H is operates, okay, on the 0 state, okay, I means electrons in the up spin. So when you're going to operate this H on the electron which is in the up spin, it is going to create a superposition of up and down spin. And if you look at further back, this is nothing but a Sx plus, correct? Can you recall this?
Yes, yes.
Means you are somewhere here. This is the state that is called Sx plus, or now I will also call it a plus state. This is 1 by root 2 and 0 and plus 1. And if you can recall now, I told you that the quantum computing, the supremacy of the quantum computing comes from the superposition. So let us say you have a 1 qubit system. So the basis states are, basis states are 0 and 1. But along with that, there is a superposition state also. That is called psi, and that is a time 0 and b time 1. So I told you that when electron spin is in the superposition state, then I need to define two complex number a and b in order to represent this superposition state psi. It means in a 1 qubit system, the superposition state contains two pieces of informations. So two pieces of information is there in this wave function. And this is what is written here. That is the Sx plus 1, nothing but a plus state, nothing but a 1 by root 2, 0, and 1 by root 2, 1. So what is doing? This Hadamard gate is very important because this is actually creating that superposition state. Because if you have large number of electrons in the system, then how you will ensure that they are in the superposition state? Because unless you're not going to put them in superposition state, there's no difference between the classical computer and the quantum computer. Only this state is going to give you the advantage of the quantum computer. These two states, they are not going to give any advantage over the classical computer. It means Hadamard gate is actually creates superposition state. Okay. And that state contains two pieces of information. And this is the reason that I'm telling the Hadamard gate is very important. And similarly, if you apply here, let us say on the 1 state, because initially when the electron is there, you never know whether it is in the 0 state or in the 1 state. So if you apply this Hadamard gate on the 1 state, okay, you can see 1 by root 2, 1, 1, 1 minus 1, and 0, 1. So this is going to be a 1 by root 2. This is 1 and minus 1. This is nothing but a 1 by root 2 and 0 and -1. Nothing but a sy negative, nothing but a negative state. So in this block diagram, you can see you are here. That is the state called H negative, no, negative state.
Isn't it Sx minus, Sugam?
Oh, sorry, yes, Sx minus, sorry.
Yeah.
Thank you. So you get the Sx minus then here, the negative state. So these two states you can superposition state you can you can create with the help of the Hadamard. So that's why Hadamard gate in the quantum computing play a very crucial role. And let me now tell you how to produce this Hadamard gate. Okay, but before that, now I can say these two states I got plus and negative. Okay, for example, this 0 and 1. Okay, they are called basis states. And sometimes we call them as the computational basis states. Computational basis states. You understand the basis states when I say, so basis state means this must fulfill, I'm right, the condition of the to become basis state. And that condition that it must be a linearly independent, correct? And you can see that 0 and 1 are linearly independent. They are orthogonals. For example, when you talk about 1 and 0, this is going to become 0. And same way here, when you're going to take this inner product is also going to be 0. And they are linearly independent. Okay, so they are also going to act like a basis. Okay, but we call them as the Hadamard basis. We call them as the Hadamard basis. And we will see that these Hadamard basis also now very useful now in majority of the cases. We will rely on the Hadamard basis instead of a computational basis. So, but now before
What is the matrix form of this Hadamard basis, plus and minus?
Yeah, here now, see,
I mean this 1 over root 2.
exactly.
So this is your plus.
Yes, 1 by root
Okay.
2, and this is 1 1, and this is going to be a 1 by root 2 and 1 minus 1.
1 minus.
Yes.
Mhm.
And this Hadamard basis is really very important because particularly I told you yesterday also that in the quantum computing, finally when the system is in superposition, then you want to do interference to increase the probability of the right result. And this Hadamard gate is actually, okay, is going to play a role there. So this is a Hadamard basis. I can say used to study interference in algorithm. Whenever you're going to write algorithm and wherever this is required, for example, think about a Dutch algorithm, or maybe a Grover algorithm, maybe a Shor algorithm. Okay, so in this algorithms, you will see that we're going to work with a Hadamard basis. Okay, it's more convenient to work with a Hadamard basis, not to work with the computational basis. So in fact, I can say like this way also. Uh, so if I say that this 0 and 1, they are the computational basis. Okay. And this computational basis, they actually corresponds to, you can see that they are corresponds to measurement along z-axis. On the other hand, these Hadamard bases, they correspond to measurement along x-axis. So they use in the study the interference pattern, interference in the algorithm. They are, I mean, if you want to analyze whether the state is a superposition or not. So I can say this is the one application where you can use. Second, also in order to prepare and also analyze a superposition state. Because let us say I already know that the Hadamard gate produce the superposition, but if there is a superposition state and you want to check whether the state is superposition or not. So for example, if you apply the Hadamard gate on the H, okay, you will see that you're going to get a 0 state. So if the system collapses to the now our corresponding computational basis, okay, then you can say no, okay, this is the no before that the state was in the superposition state. So if you want to check also whether the state is a superposition or not, then also you can use the Hadamard gate. So Hadamard basis, okay. So that is the very useful no I can say a concept in the quantum mechanics. But now come to the again how to realize H gate. Now, if you look at again, I told you again the same example, we can think about a spin in the magnetic field, and they are two states separated, and this separation is correspond to a 28 gigahertz. And if I shine a photon of 28 gigahertz exactly, then you can see that no, that probability. So that probability is like this way. So here is the time, and here the probability of state 1. So you can see that at this position, what is time? Pi upon omega. So at this time, the probability will be to get, tell me. That is called pi pulse, no? So when you apply a pi pulse, what you will get?
Spin inverted.
Exactly. You will going to get 0 to 1. But let us say, just imagine, okay, if you shine the photons only for this much time, that is a pi by 2 omega. Then in this situation, the spin is neither in 0 state nor in 1 state. It will be in the superposition state. So you can see the a very beautiful concept that just simply, and this is called a pi by 2 pulse. So if I shine a photon, so let us say 0, and I shine, let us say, only for pi by 2 time or pi by 2 pulse, then what I will get? I will get the superposition of 1 and 0. And this is how in the laboratory we realize, okay, superposition state. So actually what happens that, first of all, in the, if I write down the step now, so in the quantum computing steps, the first step that cool down the system or qubit to 10 millikelvin. Because at this temperature, Okay, generally when I can tell you that if this is the separation of, let us say, 28 gigahertz, and corresponding, if you find the temperature, then temperature will be going to be around 8 Kelvin. It means the separation, okay, is correspond to around 8 Kelvin. So if you cool down the system below a very low temperature, let us say around 10 millikelvin. Just a minute, is it 8 Tesla? No, it's 28 gigahertz. 28. I think I did one mistake, and I think you were supposed to tell me. Come back here. Yeah, here. I mean, this delta E actually be 2 time. No, this will be 2 here because G factor is there. Is 2 time mu B into B. So I think you are also supposed to know a little bit inform me if there is some mistake if you find in between. So this temperature, I mean, this energy when you calculate, that is the 2 mu B into B. So this is actually going to be at 1 Tesla. This is around 1.2 10 the power minus 4 electron volt, means 0.12 milli electron volt. And the corresponding temperature when you calculate, although temperature is a statistical phenomena, but still I can make that temperature here. So this comes out to be 1.3 Kelvin. That is the number, exact number I can say. What I mean by 1 by 3K. Now let us say that you have an electron with these 2 spins, and the temperature is, let us say, 300 Kelvin. Now at temperature 300 Kelvin, the energy is how much? 25 milli electron volt. No, I'm right? How much energy? And it means from the environment you are giving energy of 25 MeV. And for this transition, what is the energy required? Only a 0.12 MeV. And you can see that this at this temperature, the spin will keep fluctuating between 0, 1, 0, 1, 0, 1, 0, 1. But imagine that if you cool down to 10 millikelvin, okay? So at this temperature, this energy will be much, much less than the point. It will be micro EV. So this temperature will be in the micro EV corresponding energy. So it means from the environment, there is no disturbance to the spin. Are you getting this part? And now you can understand why we need to cool down the quantum computers to a very low temperature. Because you have to reach to a temperature where the thermal energy not going to cause any noise in the system. Correct? So when you are at 10 millikelvin, the energy from the environment is in the micro electron volt. This will not going to cause any. So if you cool down and wait for the certain transition time, then you will see that after certain time, all electrons will be, or I can say majority of electrons will be in 0 state. Are you convinced with this statement that you don't need to do anything? This is what is called a initialization.
Yes.
So you have to initialize your all qubits. Means you have to cool it down to a very low temperature. around 10 millikelvin, and then wait for some time. Okay, and you will find that all the qubits, at 10 millikelvin, I can tell you that around 99.9% probability is that the electrons will be going to found in the zero state. So now you can see that all the electrons are in the zero state. Electron number 1, electron number 2, electron number 3, every electrons or every qubit in a zero state. This is the first step in the quantum computing. This is the first step, initialize, and then you can shine photon on this. Okay, and this is going to create the superposition state. Okay, for example, let us say if you want to add 2 plus 3, this is a binary number. So in the binary number, it is going to be a 1, 0, and this is going to be a 1, 1. It means I want one qubit in this state, other qubit in the zero state. I want one qubit in this state, other qubit in this state, correct? So what I will do, I will first initialize everything in the zero state, and then first what I will do, I will shine pi pulse on this electron. What will it become then? 1, correct? Then I will use this one as such. Then I will shine here and here again pi and pi pulse. So they will going to become 1 and 1. Okay, so these are the our inputs. Okay. Agree? I hope so.
Yes, sir.
And this, when you're going to now take as the input, then this state is what is called 1 tensor product 0, and this is also written like a 1, 0. And then
but you cannot segregate electrons. So how do you ensure that a particular electron is being eliminated and with the pi pulse and going to?
Yes, I will show you that we can segregate it. Okay, but for the moment, just consider that I have segregated it. Okay, but
Okay.
maybe on Friday and Saturday there are 2 lectures, where I will tell you the physically how we can make the quantum computer, and there I will tell you that how we can select, okay, individual qubits. This is very challenging, but a doable task. We can select electron number 1, 2, 3, 4 like that. Okay, so I know qubit 1, qubit 2, qubit 3, and so on. I want to entangle or make a superposition of these 2. I can do it easily. So now you have 2 states, and now the quantum computing. Okay, so quantum computing, where the advantage will come to you when you're going to put in the superposition. So what you'll do now, you have this 2 qubit state, and you're going to shine pi by 2, correct? And the pi by 2 is going to put this into the superposition. And superposition means this is going to become then A 0, 0 plus B 0, 1 plus C 1, 0 plus D 1, 1. So that is the state you're going to finally get. This is the step now you need to follow. So first you produce electrons, then cool down to the ground state, that is called the initialization, and then you start doing the gate operation. So first gate operation you do, you select what you want to do. You want to add 2 plus 3 number, then I will select 4 qubits, okay, and I will initialize the 2 in this state and 2 in these states, and then I will take these 2 as the one quantum state, and then I will shine a photon on these 2 qubits together, okay, and they will be in the superposition state. So I will create another state which is the superposition state. And similarly, I will again shine here also pi by 2 pulse, and it's also going to be in the superposition state. maybe I can call, let us say this is the E00 plus and so on. And then these two, when they're going to add up, okay, so you can see that when you're going to add these two numbers, I mean, it's like it is going to be 0, 1, 2, and 3. 0, 1, 2, and 3. So when you're going to add these numbers, you're going to get a 0, 1, 2, 3, 4, 5, and 6. Okay, and this is correspond to then 0, 0, 0. I mean, I will use one also electron, 2 electrons as ancilla qubits, okay, as a carry qubits, and this is this state, okay, and this one is going to be a 0, 0, 1 state, and similarly this you can write down, and you know that the 5 is the correct answer. So 5 is the correct answer, then you will do an interference. And I will show you, I mean, so on Thursday, Friday lecture, that how we do the interference, or maybe tomorrow lecture, sorry, okay. Tomorrow itself, we're going to discuss this algorithm, where I will discuss how I can enhance the probability of 5. And then, and everything will be the superposition, remember. Everything will be in superposition. So all these results will be in superposition. So the next, let us say this is the chi, this is going to be some superposition of 0, 0, 0, plus let us say A1, then A2, 0, 0, 1, plus A3, 0, 1, 0, and so on. A8, that is going to be a 1, 1, 1. And the probability of the A5, here somewhere I can also say A5, that is the what? 1, 1, 0. Correct? No, sorry, 1, 0, 1. So you will see that key when you're going to do the measurement, okay, when you're going to operate the, when you're going to finally measure this state on this chi, then you will get 1, 0, 1 with the probability of A5 square, which is going to be maximum, maybe 99%. There's a probability that you will also get, or you can get maybe 0, 0, 0 also. But in this case, the probability will be A1 square, maybe 0.001%. And this is how you can see that you're going to say, okay, the answer is 5. But remember, not with a 100% confidence. In the quantum computing, you can never tell that this result is 100% correct. I hope these things are making sense with everybody. So I discussed that how to create a poly X gate, poly Y gate, poly Z gate, and then hard gate also.
Sir, one question.
Yes.
Sir, you mentioned this Hadamard, it's 2 qubit gates and it
No,
is
hard
used
gate is a single qubit gate.
single qubit and it is used for superposition state to make it. So when you have multiple, so you will apply this Hadamard gate in every qubit separately to
Yes,
get a
exactly.
superposition.
Yes,
Okay.
yes, that's true. Yes.
Okay.
I mean, when I say separately means this is no longer separate. This is the one state, correct? 1, 0. So I will shine the photons. Technically, I'm going to shine. So these two photon, electron number 1, electron number 2. Now they're in superposition. I will shine the photon on both, correct? Together. Of how much?
It's
Which
a
pulse?
pi by
Pi by 2.
2.
Exactly. So earlier, I was shining the light only on one electron. But now I'm shining light on both electrons, correct? Together.
Okay, so you used a monochromatic pulse laser, let's say, for photon with this pi by
Exactly.
2.
Highly monochromatic.
Huh. Okay, so if you have multiple qubits or multiple electrons, so
Yes.
how physically you are doing this? In a one single shot or
In a one
using
single
one
shot, yes,
beam?
exactly. Because see, let me tell you, this whole qubit, because their size is very small. Generally, this lies in 1 millimeter size, correct? And in this 1 millimeter size, you can create 1000 qubits or more than that, okay?
Yes.
And we are shining microwave. And what is the microwave frequency? 28 gigahertz. Now find the lambda. That is 28 10 the power 9, correct? Correct?
Yes, it's gigahertz.
So this maybe I can say like 3 upon 30 into 10 the power or 1 upon 10. So technically it's 1 by 100, I'm right? Or you can say 0.01 meter. Is already
Yeah.
a 10 millimeter, correct?
Mhm.
It means when you're going to shine the microwave, it is going to shine everywhere, am I right?
Yes.
Lambda 10 millimeter.
So
So
the
in a
laser you have a positional laser, so you can change only.
well, wait, I'm talking about the microwave. Okay. So this is the reason that
Okay.
I told you that I will discuss this part maybe on Friday. Okay. How
Okay, sure.
we going to do a selective excitation.
Mhm.
Technically, when I shine photons or radiations, they're going to fall on each electrons. Okay.
Mhm.
But when you're going to use laser, so in the case of laser, you have to use a fine spot laser so that it can fall only on a 1 qubit. But in the case of microwave, it's going to shine almost on everyone, every electrons together. But there's a technique I will discuss there. There's a technique through which I can select only electron number 1, 2. I mean, they will only respond. Photons are
Okay,
shining
even
on
in using microwave also.
microwave also. So microwave falling on all the electrons. But I will show you what techniques we use. So with that technique only, let us say I want this electron to respond. Okay. Then I will do something and only this electron will respond to that microwave.
Okay.
Okay.
Yeah, so can I ask you
Yes,
one
yes,
question?
please.
So can you scroll up a little bit where you
Yes.
wrote the tensor product? Yeah, right here, right here. Yeah.
Mhm.
So for a single qubit, we apply the microwave, the pi pulse or pi by 2 pulse, we get the superposition. But when you took the tensor product, you get the product state, right? Like 1 0, you wrote it.
Mathematically, correct?
Yeah,
Yes.
mathematically, right? But is that the superposition state? Because we have the product
That is
state.
super. Which one? No, that is not superposition state.
This is not right. 1
No,
0
no,
is
no,
yeah.
not no, 1 0 is not a superposition state.
Yeah, that's a product state.
This is just a product state. Yes.
Correct. So now when you apply the pi by 2 pulse, can you elaborate what happens then? Because now it becomes a 2 qubit
It become a
piece.
2 qubit, exactly.
Right. So now when you apply the pi by 2, so one single pulse can make both the qubit superposition.
Yes, exactly. Now you're going to shine these photons or microwave on both the poles, both the electrons together.
Right. And when we apply, let's say, so that's basically Hadamard operation. So this
Yes.
Hadamard gate for 2 qubit is having a different structure, right? Matrix wise. Or is it having the same structure?
No, it will.
Yeah, sorry, your
I mean,
voice was
so
breaking.
yes, yes. I mean, this H, when you talk about 1 and let us say 0. Okay.
Right.
So in this case, this H is going to operate mathematically on this part, correct? So this is going to get 1 by √2 state, correct? And this is going to produce, or maybe let us say this is 0 and this is 1. So this is going to produce 0 plus 1, and then you're going to have this state, correct?
Right, right.
So this is going to become 1, and this is going to become 0, 1
Right.
plus 1, 1.
Okay.
Okay, so this
Yeah.
is the actually, I mean, so if you look at carefully, then exact calculation you ask, then this is what are going to happen
I
when
see.
you're going to apply a Hadamard gate on this state. Okay, this is
Right,
what you're
right.
going to get exactly.
Yeah. But then only one qubit we have made in superposition, no? In this case.
Only 1 qubit we made in superposition. Yes,
sir.
please correct it. Yes, we are making only 1 qubit in superposition, but because both are entangled, both are going to be when you're going to make it no, when you're going to connect them. Okay,
Mhm.
so this is going to create a superposition of these two states. So
All right.
finally, you end up with these two states.
Yeah, I think above you have written superposition of 4 states. That's where I got a bit
No,
confused.
no, no. I think please ignore that part. It was just a general representation.
Okay.
Exact number is this one.
Okay, okay.
Yeah.
Yeah, it's a two product states are getting and superposed together.
That's true. Yes.
Okay, okay, yeah.
In fact, what happens that I mean, generally, when you go into, let us say, 2 plus 3 number you want to add, then this kind of quantum circuit we use. So we have one qubit here, another qubit here, and then we go for the one carry qubit and one ancilla qubit, which always kept at 0. And then, I mean, these are the two are the going to be operand in this case, and this is going to be a carry. I'm now telling you the exact, this is how we do. No? So you take these two and then apply on this. I will discuss this one. This is called a Toffoli gate, a TF. So first you apply a Toffoli gate. Then you apply a NOT gate, C NOT gate. Again, you apply another Toffoli gate, and then 2 more C NOT gate. Okay. And then this is the output you're going to get. Here is sum, and this is going to be a carry out. So carry in and carry out will become here, and this is the number you're going to finally get. Okay. So this is the actual now circuit diagram that is called the quantum circuit for a, this is equivalent to a full adder. For example, we use a full adder in the classical system. I think I told you yesterday that how you can use XOR gate. This one, I mean, so here also we use 3 bits. So A and then B, and then here we use actually one carry bit. And then you use some AND gates. So I forget that number, but whole configuration, but this is the where you get the sum out. And these two going to go into the another OR gate, and this is going to give us C out, carry out. I think it is simple now. I think I remember this will go like this way, and it will go here, and the one output here and another output here. So that is the full adder. So this is also full adder, but it's a quantum full adder. And this is also full adder, but this is a classical. They do the same purpose. So this is the exact electrical circuit. So what I was trying to show there, I wanted to avoid the because this is what I will discuss tomorrow also. These circuit diagrams. Exactly, I mean when I will run those, we will going to run some programs on the here only, and then we will see what the output we're going to get. So these are the some actual circuit or quantum circuit diagrams, which we need to little bit keep in mind. But I hope up till here, things are moving fine with all of you.
Yeah, Sugam, sorry.
Yes, yes, please.
I think you will be elaborating the full order tomorrow, right?
Yes, exactly. Yes, I will
yeah.
elaborate this one. Yes.
But just a peripheral question, like, so what does this node represent? Because for me, this is a new thing. So what does this node means here? You have put the
This one, correct? No?
those nodes, right? What are
Yeah.
they?
Even I will discussing tomorrow also this, no? Because they are
Okay.
gates, okay?
I
So
see.
these
Okay.
gates are symbols, okay? The meaning, I mean, generally we use a symbol called most significant bit and low significant bit, okay? So these nodes are made at those locations, but they have a meaning, okay? I will discuss tomorrow when I will
Sure.
discuss.
Yeah, no
in
issues.
detail.
Yeah. We will discuss tomorrow, right? Yeah.
Time is also up, I think. Maybe I think I will like to take 10, 15 minutes more. At least we can finish what we targeted. Okay, so we are done with the one qubit gate. Similarly, we can have a 2 qubit gate also. So in 2 qubit gate, then we will talk about some important gates. For example, C0 gate. After HADMAR, this is another gate which is very important, but this is a 2 qubit gate. This can be applied directly on the these two states. So this can act on both together. And this is called as the controlled NOT gate. This is called controlled NOT gate. And this is actually equivalent to a XOR gate of the classical system. So when I say control NOT, okay, so control NOT means this is a controlling, okay. And so there will be a one qubit going to be called as the control qubit, and other qubit going to act as a target qubit in this case. So maybe I will not go to the mathematics because then okay, little bit now. This unitary operator for this kind of any 2 qubit gates in general, we can represent is like a I2, O2, O2, and U2. Okay. But this is going to be a 4x4 matrix. This is in the 4-dimension, 4-dimensional Hilbert space. In the case of U, we use C0, and this is going to be I2, O2, and O2, and here it will be a C0. Sorry, this is going to be not only. So this is going to become a C0. So in general, when I writing this, let us say I2, O2, O2, and U2. So I2 is identity matrix. Okay, this is 1, 0, 0, 1, and 0, 0 matrix, that is 0, 0, 0, 0. Now this U2 play a very important role. See, if U is become X gate, okay, then this gate is going to be called either C0. But if this U is going to become Z, so X nothing but a 0, 1, 1, 0. Z nothing but a 1, 0, 0 minus 1. So in that case is called a CZ gate. And if the U become S, I will talk about this further. I think I forget to talk about this S gate, but then this is called a C phase gate. So you can see that here, this NOT will simply going to be act like a X gate. And this is going to behave like then this I2 nothing but a 1 0 0 1, and O2 means 0 0 0, and O2 is again 0 0 0, and X is what? X is actually a 0 1 1 0. So this is what is called the C0 gate. And what it does? So in the C0 gate, now I can not talk about the quantum circuit of this 2-qubit gate. So you have now 2 bits here. So one is A, other is B. Okay. So this is going to here act like a control bit. And this is acting like a target bit. And this whole C0 gate act like an XOR gate. So if you look at the truth table of XOR gate, what this is, A, B. So if 0, 0, then output is what? 0. When you have 0 and 1, output is 1, correct? When you have 1 0, output is 1. When you have 1 1, output is 0. This is what this C0 gate also does. So the C0 gate circuit diagram we represent by this symbol. So this symbol is actually, I mean, in short, we represent by this. This node, okay. Now, I mean, this bit on which the node is there, that is called the most significant bit. And the line where the node, that is called the least significant bit. So this will define which qubit is going to act like a control bit and which going to act like a target bit. So what it does, okay, this simply does a very simple task. Okay, this is going to flip the spin, okay, depending upon the value of the control bit. If control bit is 1, then it will going to change the target bit. So truth table for this one is like this, A and B, and the output you're going to have a A here, and the output here is going to be a B modular addition E. So this is modular 2 addition. I hope you are aware with this modular 2 addition symbol. Everybody? Means when I say modular B plus A, technically means when you have a 0 plus 0, it will become 0. When you have a 0 plus 1, it is going to become 1. 1 plus 0 is going to become 1. And 1 plus 1 is going to become 0. So here you can see 0 and 0. Now this output is A, and also output will be here. This. So this is going to be as such, it will remain 0. And this is also going to be 0. 0 and 1, this is going to be 0. This is going to be 1. 1, 0. Now you can see this is a control bit. This is controlling the target. Now when the control bit is 1, be careful now. When the control bit is 1, then it is going to flip the spin of the second qubit. Then this is going to become 0. Of course, this remains 1. And here it is going to become then 1. And this is again 1, and this is 1. Then again control bit is 1. Then it is going to flip this, change the target bit. So this is a 1 and this is become 0. So you can see it is the same XOR truth table, but in the quantum mechanical term. And this is what is called the C0 gate. The C NOT gate is one of the most important 2-qubit gate. And in one line, I can say it going to flip the second qubit. This is a second qubit, or you can call target qubit, only if the first qubit or the control qubit is in the one state. Otherwise, if not, then it will leave the target qubit as such. This is what is called as the control NOT gate. All right, clear this part? And we will see the importance of this now a C NOT gate, because if you want to create entanglement, so you cannot do entanglement without C NOT gate. And this is what we will learn, how to entangle 2 qubits together. So we will see, we're going to use hard-mode gate and C NOT gate together. And this way I can create a entangled state, or you can call also a Bell state. So give 10 more minutes, because 2-3 more gates are there I need to discuss, so that tomorrow we can directly come to the quantum circuit and quantum algorithm. So in these 2-qubit gates, there are other gates also, which we need to little bit work upon. And one of them is called, second is called control jet. Control jet gate. So this control jet gate, in fact, I can say control jet gate, and one is called control phase gate. These two together can be represented in this format: I2, O2, I2, and R theta, that matrix which already you have mentioned, or maybe phi. And when this phi is become pi, then this is become a CZ gate. And when the phi is pi by 2, then this is going to become a C phase gate. Anyway, before I discuss this two part, because this control NOT gate is very important. Anybody want to ask any question on the control NOT gate?
Sir, how you relate this with the Bell states here?
How related
So
to the
could you-
Bell state? Okay,
yeah,
okay.
could you please
Let me.
explain more?
Yes. I mean, so using H and C NOT gate, we can create Bell state. Bell state क्या होती है? Entangled state, correct? For example, this is circuit diagram. I can tell you. I apply H gate first on qubit 0. I take 2 qubits, 0, 0, and then I apply C NOT gate. So what is happening now here? Look at now. H operate on the 0. You will get 1 by 2 and 0 and plus 1. So at this location, you will get this state. No, this state maybe can call phi. So the state here will be a phi now. So now for the C NOT, you will get state what? You will get a state phi tensor product 0, correct? So that state, I mean, in the combination of these two, then is going to like this one. So this is going to be a 1 by root 2 and 0 and 1 and tensor product 0. This is going to become 1 by root 2, 0, 0 and 1, 0, correct? This is superposition state. This is not entangled state, correct? So now on this state, the C not going to operate. Let me call this as the psi state. So C not going to operate on the psi state means this is going to operate on the this state. So 1 by root 2 and 0, 0 and 1, 0. So this is going to become then 1 by root 2, the C naught operating on 0, 0 and C naught operating on the 1, 0. Now look at here, what is happening? So this is the control bit, na, correct? And this is the target bit. In this case, this is the control bit and this is the target bit. Now in the first case, since control bit is already in 0 state, so this is going to become 0, 0, fine. In the next one, the control is 1. So it means what it will become? 1, 1. And you can see this is the Bell state or entangled state. I hope somehow clear this part.
Yes, this Bell state will be the 4 basis states in when we operated 2 qubits,
No,
right?
I mean, this is also basis state, no? This is also the
Yes.
Bell state. No? Bell state means entangled state. Mathematically means if you cannot express this as the basis states. If you cannot express as the no, tensor product of the basis states, then those states are called the entangled state. So you can't, for example, here in this case, in the first one, look at here. So you can express this state 0, 0 and 1, 0. This in combination, this is not a Bell state because you can express as the tensor product of the two basis states, correct? One is the plus, another is the 0. But you cannot do here. You can never express this as the tensor product of the basis states. And when you mathematically, I'm telling you, if you cannot express a superposition state as a tensor product of the basis states, then such states are called as the entangled state. Because in this case, these qubits are entangled, they are correlated. If you do something to this state also, I mean, when you're going to do something to this state, other state also going to be disturbed. I mean, there are two electrons, no? Electron number 1, electron number 2. If you do something with this electron, other electrons also going to respond accordingly. We will talk about this, no? Tomorrow, of course, is all day for this Bell state and entangled state. But this is how answer for your question. This also tells you the importance of the C0 gate. The C0 gate actually, in combination with the H gate, help you to create the entangled state or Bell state. And without entangled state, you cannot do anything in the quantum computing because we need to correlate all the qubits together.
Okay, so for Hadamard gate, if you use pi by 2 pulse, then you get the superimposition.
Exactly.
And
Yes.
after that, for C naught, what you do to
Okay.
get this entangled state?
Okay. Maybe because that will take some time. Then maybe I can discuss that tomorrow, right?
Yeah, that's fine, no
Yeah.
problem.
Okay. Quickly, what I'm trying to do that can quickly, at least mathematics of the all gates I can finish. Okay. Then tomorrow again, maybe we can discuss the how to realize the C0 gate, no, physically, correct?
Yes, sir.
I will
you.
show. Yeah.
Mhm.
So this is the I was discussing about these two gates that is called the phase gate, not those called are phase gates. And I told you that those phase gates we can easily make, okay, with this I2, 02, 02, and here is the R5. And I told you that if the phi is actually pi, then you're going to get a CZ gate. And when phi equal to pi by 2, then you're going to get a C phase gate. And how we can represent? You can see that CZ gate or CZ gate, for example, simply, okay, I mean, so in principle, this one is nothing but a 1, 0, and 0, 1. And this is 0, 0, 0, 0. This is again 0, 0, 0. And this R5 is what? 1, 0, 0 e power I5. And you can see that the CZ gate will be equal to what? 1, 0, and 0, 1, 0, 0, 0, 0, 1, 0, 0, 0. And when you put phi, then the value become -1. And what does that then it does? Look at see if CZ gate. Now when you're going to operate on, okay, so CZ gate affect only 1, 1 and only 1, 1. Okay, nothing happen and nothing happened to other states. Similarly, you can see the C phase gate. What did you put? Pi by 2. So when you put pi by 2, then what the value then? It is going to be a 0. So here it will be a simply iota, correct? That is C phase gate only. And both, even C phase gate and CZ gate, both going to affect only this state 1, 1. They're not going to cause any change on the other gates, other states. So little bit I'm moving faster just to make sure that we finish our gate today. And the fourth one is called another very important, that is called swap gate. So swap gate means if you have, let us say, electron number 1, or maybe I can look like this, right? Like this, qubit 1, qubit 2, qubit 3, and qubit 4, and qubit 5. Now see, there is one problem. And now when I will show you the superconducting qubits, and this is particularly used by the IBM company. So it is a limitation. In the superconducting qubits, only gate operation can be done to the 2 adjacent qubits. I cannot apply gate on the Q1 and Q3. This is not a problem in the ion trap, but in the superconducting qubits or platforms, I can only apply gate only on the neighboring, okay, on qubits. If I want to entangle, let us say Q1, Q3, I cannot do it. If I want to entangle Q1, Q4, I can't do it. So let us say I want to create a superposition, okay. So let us say I want to goal is that want to apply, let us say some 2-qubit gate, maybe like C naught gate, maybe like CZ gate, okay, on Q1 and Q4. Now see, in the IBM or all these company which are using the superconducting qubits, okay, you cannot do this. You can't apply 2-qubit gate between 2 qubits which are not adjacent. In all this IBM, you can apply 2-qubit gate between physically adjacent qubits only. So for example, in these two. So what we can do then, we can swap. What I will do, I will bring this Q4 to Q3 and then Q3 to here. Then finally you can see that the Q4 will be here, and then I can apply the Q1 and Q2 and this gate on this. This is called the gate swapping. So when I swap this gate, so the Q3 will go here and Q4 will come here. In the next step, when I do here, then the Q2 will come here and the Q4 will come here. And then this is called, this is now you have these 2 qubits in the physically adjacent. This is called the swapping, okay? And this can be done by a gate called the swap gate. Understood the meaning of the swap gate? And this is the just for the moment, just write down. Maybe we can discuss tomorrow in much more detail. But these are the some important 2-qubit gates. Okay. And similarly, maybe I will share my notes today. You can also study about 3-qubit gates yourself. And in 3-qubit gates, it's required. I mean, because particularly 1 qubit, which one gate which I need, that is called the Toffoli gate. I just mentioned that this full adder, okay, how it works. So we need a Toffoli gate. It's also called CC NOT gate. That is called the control NOT gate. This is a 3-qubit gate that applies a NOT operation to the 3rd qubit, a 3rd target. So what is here now? There are 3-qubit state here. So in this, there are 2 control bits and 1 target bit. And then when target bits are, let us say, now let us say like this way. So it is 1, this is a 1, and this is a 0. Then at the output, now this symbolically we represent like this way. So there are 2 nodes, okay? So 2 nodes means there are 2 most significant digits, correct? And 1 least significant bit. So it means these 2 are control bits. So here, when you're going to use this like this way, then when both are 1, okay, then only the spin will flip. Think like it is like an AND gate. So what is the AND gate? 1, 1, then you will get a 1. And if you have a 1, 0, 0, 0, 1, 0, 0, 0, 0. Same here also. You can see that if you get a 1 here and 0 here and 0 here, then in that situation, of course, these control bits will remain as such, but here nothing will happen. It also going to remain the same. Like this way. So it is like an AND gate. So 2 control bits, when they are going to become 1, when they both are in the 1 state, then only the target qubit is going to change or flip its spin. Okay, that is called the Toffoli gate. We will see that. And the last one is called a Fredgin gate. This is also called a C-swap, control swap gate. So Fredgin gate, or you can say control swap gate, is again a 3-qubit gate. And this is going to swap. This is going to swap second and third qubit. They are the target. So here you can see there are 1 control bit and 2 target bits. And the symbol we use this one. Okay, this symbol say I just remind myself. The swap gate here, the symbol for this is this one. Okay, only 1 cross, and that is the first symbol for the this one. So this is symbol for this, and it is again just what you will do. If you look at the procedure, then it will check the first qubit. That is a control bit. If the control bit is, let us say, 1, then it is going to swap these two. So let us say this is 1, and this is, let us say, 0, and this is a 1. Then what is going to make it? It is remain 1, and this is going to become 1, and this is going to become 0. They are swapped. But if it is a, let's say, control bit is 0, and then here it is a 0, here it is a 1, then it will do nothing. No swapping will take place. So swapping will take place only when the control bit is going to be 1. So this one control bit going to control 2 target bits. That is called the control swap. And this control swap is very useful, because this is going to allow you to swap 2 quantum data registers in the register only when the condition is met. And where I can use it, I can use in all the quantum algorithm where decision making is involved. This is widely used in the machine learning. Are you getting this point? Simple, like I can give analogy. For example, let's say you think about a train track. So if you have a signal, no, signal is going to act like a control bit. And I say that when signal is red, so red is equivalent to 1. Sorry, red is equal to 0, let us say. And let us say green is equal to 1. I'm just giving an example. So let us say if the signal is red, then these 2 tracks will not change. No, I want to change the track of the train. So this track will not going to change. Okay, if the signal is red, but if signal is green, means 1, then the I can say that the track will change. Okay, I hope you got the idea what I'm meaning by the C swap. So there's 1 control bit and 2 target bits. Okay, so this 2 target bits going to swap or exchange. So that's all. I mean, so I think these are the most lengthiest topic, because since I not only discussing the mathematics, but also discussing how to physically realize these quantum bits. And this is the reason that I think we took a long time today to finish. But I think from tomorrow onward, we will try to stick to our timing. Okay, so please let me know if you have any doubt up till here. Already we have taken 26 minutes extra, but still if you have some questions, we can discuss. Today's lecture was more or less mathematical. Of course, we discuss laboratory case also, but most probably from tomorrow onward, again, I will try to, because this was the only lecture where mathematics was required too much. But from tomorrow onward, you will see less mathematics, and we will more try to see things physically.
Sir, for superconducting qubits, why we can't apply gates to far end rather than
Yes,
the
yes, yes.
adjacent end?
But only 2 days. I mean, so I will discussing. I'm going to have one complete lecture on the superconducting quantum computers. Okay. So there, our task will be only to discuss these things only. Okay. Why we cannot, no? I mean, it is because that the resonator, no? I mean, if I use the word, then you will see what I'm talking about, because there are no resonators which going to couple with the qubits. And because of that, the limitation is there, no? That only two nearest qubits can couple together.
So will you please provide the video of on the
Yes,
unit
yes,
on
yes.
the YouTube
It
channel
will be available. Yes, it will be available soon. Yeah.
of yesterday also?
Okay.
Okay, thank you, sir.
And I will share my notes today also. Then you can please go through this, and I will send you today assignments, and please try to solve those assignments now based upon the quantum basics and little bit on the quantum gates.
Yes. Sir, is there any possibility the in notes which you are going to provide have a detailed mathematical description also?
I can make it. Okay, I will first share to you, and then maybe then I can modify my notes later on. Okay.
Yes, sir. Thank you, sir. Because these needed to at least go through twice, thrice then.
Definitely.
Yes, sir. Thank you, sir. Thank you so much, sir.
Yeah,
Okay.
Sugam, I hope we can have some programming session also,
Yes.
since we are doing the.
Yes. 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 Yes.
Yeah,
I'm plan to show you the kiss kit.
correct. Yeah.
Yeah.
Yeah, we look forward to get that training as well. Yeah.
Yeah.
Thank you.
Okay. So if nothing else, then I think I can stop. Sunil, are you here?
Yeah, yeah,
Okay.
Sugam. Yeah, if there are no questions, I think we will stop it here. I'm stopping the recording now.
Okay.